Good afternoon, everyone, and thank you, Professor Sanchez, for the great introduction. My name is Danoglidis, and today I will try at least to keep you entertained due to the lunchtime and that we had this trouble with my presentation. And I will give you an update about our research, about the convergent approach for monitoring the fluid-to-solid transition in 3D printing using adaptive rheology and electrochemical impedance spectroscopy. And actually, today I will go a step further of our research about sensing materials. First of all, as the audience here knows, the 3D printing concrete requires a characterization of the printability of the fresh cement-based mixture. And when we talk about printability, we mainly talk about the flowability of the material and the buildability of the material. And these two parameters can be characterized if you characterize the time of initial setting of the material. And except of the regular concrete, we know that for a 3D printing concrete, we need a rapid setting. So the layers can be very quickly deposited and adapt an acceptable strength, the already known Gring strength. So the next layers can be properly placed on the structure. One of the properties that characterize the flowability is the viscosity, the material's ability that indicates the resistance of the material to flow. And also for the buildability, as I already mentioned, the Gring strength, which is a compressive strength at the plastic stage. So my question here is, of course, we can measure these properties, the viscosity by using a rheometer, or the Gring strength by conducting uniaxial compression tests. Can we monitor? Can we predict these values? And here the electrochemical impedance spectroscopy comes into the game. For all materials, actually, and especially when we talk for complex fluids, for example, cementitious materials or concrete, then we talk about materials that includes two phases related to the electrochemical phases. And we talk about the resistive phase and the capacitive phase. For many years now, we talk about sensing, self-sensing concrete, strain-sensing concretes, and concrete with new functionalities, and we basically refer to the resistive phase. And the resistive phase actually is the ability of the material to resist an electric current through it. Actually, we talk about the electrical resistivity or electrical conductivity. But when we talk about the conductivity, we need to establish a conductive network within the matrix. That's the reason that when we talk about sensing, self-sensing concrete, smart concrete, we talk about electrically conducting nanocomposites. So there is a limitation here, that we need a conductive network to monitor the behavior of the material, the morphology of the material, the properties, the response of the material. Can we overcome this? The capacitive phase is the ability of the material to store electrical energy. And on the other hand of the electrical conductivity, this phase is independent on the need for the presence of an electrical conductive network within the matrix, because we talk about energy storage and not energy transport. The capacitive phase is actually characterized by the true material property, the dielectric permittivity, which indicates the energy storage capacity of the material when we talk about the electrical energy. So in this study, we used dielectric permittivity data and correlate dielectric permittivity data with the time of setting, viscosity, and Gring strength. And I will walk you through this in my presentation to see if we can use, finally, electrochemical impedance spectroscopy to predict, to simulate the properties. So, in this study, we prepared cement paste and mortar using an ordinary Portland cement type 1 and standard sand, and we also used nanomaterials carbon nanotubes. And to showcase the ability to monitor changes in the properties at the fluid state and the early age stage, we used two different procedures of carbon nanotubes. As received carbon nanotubes in a form of bundles, and monodispersed carbon nanotubes. We applied the controlled ultrasonication energy to thoroughly disperse the as received nanotubes into monodispersed nanomaterials. The experimental program, our experimental program includes regular tests. For example, for hydration and setting time, we conducted isothermal calorimetry tests following the ASTM. The time of setting, we used the VICAT apparatus to determine the time of setting. And we also measured the electrical properties of the fresh material through electrochemical impedance spectroscopy measurements. We also conducted rheological tests using a hybrid rheometer, that measures the viscosity of the material and at the same time the dielectric permittivity through an impedance analyzer which is connected with a dielectric accessory to the rheometer. And also we evaluated the green strength of the material after the initial setting by conducting uniaxial compression tests. And for all these experiments, we use the dielectric permittivity data to see if there is any correlation between the time of setting, rheology, viscosity, and green strength, and electrical data. First, I will start with the hydration kinetics of cement paste. I want to highlight here that in the first part of my presentation, I'm talking about the neat cement paste without carbon nanotubes within the matrix. And here we see the rate of heat evolution through the hydration time curve of an ordinary Portland cement of 0.4. We see the four hydration states: the initial hydrolysis, dormant period, hydration, acceleration, and deceleration. And as per the ASTM, we are able to identify the time of initial setting of 152 minutes and the time of final setting 300 minutes following the ASTM. And we also determined these times of initial and final setting using the VICAT apparatus following the ASTM 191, and we see that the results are in a good agreement. In this slide, I included in the bottom part, actually, of the slide, the permittivity values of the ordinary Portland cement paste during the hydration time. We conducted these measurements during hydration. And we see that permittivity starts to decrease throughout the hydration time. This is something that we expect because once the material gets hardened, the energy storage capacity decreases because there is less pore connectivity, and the size of pores actually become smaller. So the material exhibits a lower ability to store electrical energy that we provide through the impedance analyzer. So from this curve, are we able to identify changes in the hydration kinetics? Of course, no. But please see the changes in the rate of the permittivity readings. we calculated the rate of permittivity change by using the previous readings. And here in the red curve, I show you the rate of permittivity change values through the hydration time. We see that starting at 0 and up to this value, which is a single point, we have a decrease of the rate of permittivity change. After this point here, we see an increase up to a second point when then the material reaches here the highest of the rate of permittivity change and then drops and reaches almost a value of 0. If we will correlate the rate of heat evolution curve with the rate of permittivity change curve, we see that this point is identified, which is the initial time of setting, is identified by the rate of permittivity change curve. Also, the second point, which corresponds to the time of final setting, can be marked on the rate of permittivity change curve. So, from this slide, we can safely actually conclude that we can use the rate of permittivity change to identify the time of initial setting and time of final setting through the single point identifications. In the next slide, I will show you the curves from the viscosity through the hydration time and the dielectric permittivity through the hydration time. The viscosity curve is the blue color curve, and the dielectric permittivity, the red color curve, that were obtained using the hybrid rheometer, which was connected to the impedance analyzer. And what we see from the curve, we can identify 3 stages. The first state, which is the fluid state, the viscosity increases while the dielectric permittivity decreases up to this point at a certain, if I may say, rate of change. And in the transition state, the fluid to solid transition, we see that viscosity increases at a higher rate, while the dielectric permittivity decreases at a higher rate as well. Once the material reaches the final setting and we have the solid state, then we see that the viscosity readings are constant and the dielectric permittivity readings are constant. So we see a good correlation here between the viscosity and permittivity values. However, I want you to see the change of the viscosity readings. The range of the viscosity measurements is from 0 to 1 Pascal times a second, while a higher difference in the dielectric permittivity is observed from around 75 to almost 450 farads per meter. To further elaborate our results, we calculated the rate of viscosity change and the rate of permittivity change of this Portland cement. And in this slide, I will show you the rate of viscosity change in this blue color curve. And what we see is that the change at the fluid state is negligible. There is a small jump at around the time of initial setting, and then during the fluid to solid transition, the viscosity, the rate of the viscosity change decreases, reaching the value of 0. So, from this point, from the time of initial setting, we identified a rate of viscosity change of 0.65. This is a very small value and a negligible, if I may say, value. The rate of permittivity change is included here in this slide, the red color curve. We see during the fluid state a small change of the permittivity. However, at around the time of initial setting, we identified a rate of permittivity change of 6.5%. And I included here a threshold that is according to the literature. According to the literature of cementitious materials, a change of a property of 5% identifies a material as a smart material, as a material that can detect a change on its structural shape. So from the rate of viscosity, we see from 0.65%, which is well below this 5% threshold. However, we can exceed this threshold by using the rate of permittivity change. So we can use these readings as a self-setting function to identify the time of initial setting of fresh cement-based mixtures by using just some electrical readings without having an isothermal calorimeter or a Vicat needle. So, in the next slide, I will continue. These results are for an ordinary Portland cement paste with a water-to-cement ratio of 0.4. Can we use this technique for other mixtures? In this slide, I included the Portland cement paste reinforced with the carbon nanotubes. We use carbon nanotubes, the dispersed carbon nanotubes, at a low amount of 0.1% per weight of cement. This concentration is based on our previous work that we found that this amount of 0.1 increases, yields the highest actually increases in the mechanical properties. And we see the rate of permittivity change in the purple color curve and the rate of viscosity change in the yellow color curve. First of all, we identify again that the permittivity change can be used to identify a single point of a time of 125 minutes, while the viscosity is very low. The same here for the final setting. We see that the ordinary Portland cement paste, reinforced with the carbon nanotubes, has a time, let's say, final setting of 245 minutes. How can we know that this is the initial and final setting? We actually conducted isothermal calorimetry tests and Vicat needle tests, and we convert the results, and we see that the values obtained from the permittivity test are in a good agreement with the Vicat apparatus tests. And a second observation here is that the addition of carbon nanotubes, well dispersed, shifts to a lower initial and final setting time. That means that the material results, the addition of carbon nanotubes, results in a slight acceleration of the hydration process. And the reason is that we use a nanomaterial with an extremely high surface area. We talk about a surface, we talk about a surface area of more than 500 when the cement grains are around 130. And this is a case for the dispersed nanomaterials. But what happened if we use agglomerated bundles? We see that the ordinary Portland cement which has received carbon nanotubes, the initial time of setting is delayed, 180 minutes. The same for the final setting time here. So there is a deceleration, actually, of both the initial and final setting time. This is because we use an agglomerated material that creates a delayed hydration process. But also, I want you to note here that the change in the dielectric permittivity is lower compared to the change of the dielectric permittivity of ordinary Portland cement. Let me here, yes. And So why is that? When we use agglomerates, nanomaterials, they act as very good, if I may say, absorbers of electrical energy in the form of capacitors. We know that the capacitor includes electric conductors within an insulating material. When we use agglomerated nanotubes, then we actually introduce these large-size capacitors able to absorb electrical energy. That means that the rate of change of this electrical energy is much lower. The material hinders the change of the electrical energy. From these results, we see that, yes, the dielectric permittivity can be used to identify the hydration process of plain and nanomodified cementitious materials and actually cement pastes. What happened if we reach the initial time of setting? We actually conducted uniaxial compression tests at the time, forming specimens at the time of this initial setting, 152 minutes for the ordinary Portland cement. We use the same time for mortars. And in the left part of the slide, we see the load to deformation curve. We calculated the green strength as using the maximum load. And we also used the permittivity readings up to the initial time of setting by constructing the rate of permittivity change through the time, the curve, and calculating the area under the curve. This is the so-called electrical energy density and can provide some interesting information if we will compare it with the green strength. Specifically, high green strength values and high electrical energy values can provide an improved ability of concrete to retain its own shape after casting. And here I included actually the results of the ordinary Portland cement and the mortars reinforced with the carbon nanotubes. We see that addition of carbon nanotubes increases by 15% the green strength of the material, and at the same time, this nanomodified mortar exhibits a 15% decreased electrical energy density. That means that the material is more dense, does not store that high amount of electrical energy, and exhibits a higher compressive strength. Now, if we will use the agglomerated materials, the carbon nanotubes, we see the opposite pattern. Actually, the electrical energy density of the material increases this time by 30%, and at the same time, this mortar exhibits a green strength lower by 13%. To conclude with the presentation, from the results, we see that there is a potential to use electrochemical impedance spectroscopy measurements, and especially dielectric permittivity, as a self-sensing function to identify the time of setting, initial and final, and see changes in the viscosity. And also, by using these readings, we can identify changes in the green strength of the plain material and the mortar nanocomposites. I would like to acknowledge the financial support of the University Transportation Center for Durable and Resilient Transportation Infrastructure of UTA, and thank you very much for your attention.